All right, so today we're going to take a look at 10.5, which is the last section in Chapter 10. And these are going to be counting problems that have specific language in them that uses the words not or the word or. And to start with, I want to talk about the complements principle of counting. So the number of ways that a certain event can occur is the total possible occurring ways minus the ways it can't. Now, we've kind of almost used this property, but we haven't talked about it yet. And there's three formulas, all interchangeably, that can be used to go along with this idea. Okay, so if your event is called A, then do you remember what the notation for a complement of A would be? What's that? No, it's notation involving, it's not a word. It's a notation involving A. How do I designate the complement of A? We did this back in Chapter 2. I know it's been a long time. What was it? A prime. You guys remember that? Complement of A is A prime. It means everything that's not in A. So if A is the event that I get a face card, then A complement would be the event that I don't get a face card. Make sense? It's just the opposite kind of, event happening. I'll say it that way. All right, so the number of ways that these two events can happen are related. So if we want to know the number of ways that event A can happen, this is the number of ways in the entire universe or universal set or sample space or whatever language you want to use, the number of ways something can happen, total, minus the number of ways that what we want to not happen would happen, a complement. And this formula can be rewritten in a variety of ways, okay? So I could have rewritten it to appear this way with the complement on the left and the original set on the right, original event on the right. Or if you'd like, you can talk about the number of ways the event happens, plus the number of ways that the event doesn't happen would be the total number of possible events, or total number of possible outcomes. We'll say it that way. You guys recognize this is all the same formula, right? There's very little even algebra related to this, but all I'm doing is adding and subtracting things from different sides of an equation. There are different ways of sort of thinking about it, and these are the idea of complements. And we're going to use the idea of complements through this entire section, and I want to preface that what I'm going to show you in class is not exactly how your book is going to present it, but my strongest suggestion is for you to rewrite it this way as you work through it. So let me show you what I mean. Are we okay with this slide writing? Leah, not quite finished? Okay, then let me pause for a sec. Sorry. You can move if you'd like. It's not as loud as over here. You're talking about that buzzing, right? Yeah. You can come sit over here. You're still going to hear it, though. I know.
Okay.
All right, are we good to go? All right. So let me show you what's going to actually happen. So first of all, we came up with this number last time. There are 2,598,960 possible 5-card poker hands. You guys remember that one? Vaguely, that was the number we came up with. And we're going to ask several questions based on that. And the first one says, we want to find out the number of ways we can have a hand of cards, rather, that has at least one card, not a club. Okay, so you're seeing some phrases that are going to be very common in this particular section. The phrases are at least something happening, at least one, and you're going to see the word not. Something doesn't happen. Now, this question is exactly what would show up on your homework or whatever. What's not going to show up is the part that I put in parentheses. So it is highly advisable for you to actually fill in what I'm about to do in parentheses as you work each one of these problems, because it's going to make finding the answer to the problem a lot easier. Okay? So what we're going to do is we're going to talk about what the opposite or the complement of this description is. So this description says that at least one card is not a club. What's the opposite of that?
Exactly.
Yeah, say that.
That is.
Not quite, Leah. Ethan, say that a little louder. All the cards in your hands are clubs. If you have a hand of cards that's all 5 clubs, then it won't satisfy this condition. Agreed? If you only have 4 cards in your hand that are clubs, it will. So the opposite of this condition, at least one card not a club, is all clubs in your hand. Does that make sense? The logic on this is going to be the trickiest part for getting these right, because once you establish the logic, it's going to be easier to do the problems because you've done them like them already before, back in 10.3 and then in 10.4 as well. So this is the complement of a hand that's all, I'm going to even put the number in here, all 5 clubs. So if we have a hand that's all 5 clubs, it would not match this description. So if you think about it, what we just decided is that this part right here was A, and this part that I just wrote right here is A complement. Okay? That means I can use those formulas, any one of them I'd like, from the previous slide. And so the one that I'm going to actually use, I'm going to use, I guess the way that I've written it is either the first one or the second one, the one with the subtraction. Because I actually know that the number, this right here, this 2,598,000 number, this is the U. This is the number in the sample space. This is the number of different ways that I can have a 5-card poker hand. So what I'm going to do is I'm going to actually use the formula that takes the number of A, which is what I'm looking for, and I'm going to find it by doing the number of items in the whole, kit and caboodle, and taking out the number of items in my complement that I just described as 5 clubs. So I know the first number. I know N of U. It's 2,598,960. And you'll probably have it memorized by the time we're done with the lesson today because we're going to keep using it. But I need to figure out the number of ways that I can get the complement. That is, how do I get a hand that's all clubs? We've done something similar to this. How do I get a hand that's all clubs?
There are 13 clubs.
There are 13 clubs. And how many do I need to pick? 5. Austin, is it a combination or a permutation?
It's a combination.
It is a combination, right? Do you guys, why is it a combination? Because order doesn't matter with our hands of cards. So this is a combination, and I'm going to select 5 of them. Okay, does everybody remember that? Those pieces? Okay. Now, 13C5 is actually a combination that we've done before. We'll do it again here. And since it's been a couple days since we've done factorials, we're going to do it with factorials. If you really wanted to do this with your Pascal's triangle, you could. But I didn't ever write the triangle down to 13, row 13. So I'm not sure that that would be something that I would want to go that far into the triangle for. So I would be more apt to use permutations on this, or I'm sorry, factorials on this one. So I have 13 factorial on top. What goes on bottom?
5 factorial and 8 factorial.
Right.
Which is 13 minus 5.
Yeah. Okay, so is everybody all right with that particular portion? Okay, great. So I've still my 2,598,960. And we're going to find this piece here right now. So I'm going to write the 13 out till I get to what? 8. So I have 13, 12, 11, 10, 9, and 8 factorial. There's my 8 factorial. And I have 5, 4, 3, 2, and 1. Okay, so the 8s go, and then what? How about 4, 3, and 12? Could I do that? 4 times 3 actually is 12, so I'm going to simplify it with the 12 on top. There's actually something else I can do kind of like that on bottom. What can I do? 2 and 5 are 10, so they can reduce to the 10 on top. So what's left on top is actually just 13, 11, and 9. So what is 13 times 11 times 9? 1287. All right, so what is 2,598,960 minus 1287? It's still 2 million something. What else? Okay, does that match? Got another. I got a nod. Okay, good. Okay, any questions on that? So, once I got to the point where I recognized I had 5 clubs that I was looking at, the problem became something I've done before. The real point in this particular section is figuring out what that complement is. Once you figure out the complement, you're not doing anything new. Okay? So let's take a look at another one. Cards of more than one suit. What's the complement of that? Right, so all the same suit, right? Now we don't know in particular which suit, so we'll have to take that under consideration. But we do know that we've got either all cards or all clubs or all diamonds or all spades. That's the complement. So again, this piece right here is A, and this piece right here is a complement. So the formula sets up the same every single time. I take the number of the way I'm looking for, which is number in A. I'm sorry, A. Let me write it right. I take my number in my U minus the number in A complement, which is the part that I'm going to be able to calculate pretty straightforward anyway. All right, so the number in U is the 2,598,960. That's our new favorite number. And then how do I get all the same suit?
All the same suits, isn't it? There are 4 suits, right?
Mm-hmm.
And another card that has 1 suit.
Say again?
And I'm looking
For them all to be in one suit. Is that what you said?
for...
That's right.
Isn't that 4C1?
Not for, well, we're going to have a 4C1. What does 4C1 tell us we're going to do? I mean, I know you know what the number is, but what does 4C1 do for us? It picks the suit, right. 4C1, or you could just put the number 4, picks the suit, because I have 4 suits to pick from, right? So that doesn't actually pick any cards. It just picks the suit that I'm working in. Then I have to pick the cards. Right, and we actually did 13C5 on the previous slide, didn't we? So I don't know about you, but I don't want to recreate the wheel if I just did the problem before. Okay? So there's no reason to actually go through the 13C5 again because you guys know how to do that. But I've got the 2,598,960, and then 4C1 is 4. We've worked through that idea before. And it'd be 4 times 1280, was it 87? 1287? All right. So what is 4 times 1287? It's 5,000 something, right? What was it? 148. Okay. And then we need to subtract 2,598,960 minus 5,148. Okay. Is that all right? Okay, see, again, once you determine the complement, it's not anything different. I mean, there's a subtraction feature, I suppose, but you guys know how to subtract. That's not a concern for me. But the actual factorial process is all the same thing we've been doing. All right. At least one face card.
What's a face card?
What's a face card, guys? King, Queen, and Jack. Okay. So what is the complement of having at least one face card? No face cards. Okay, does that make sense? If I have a whole hand and there's no face cards, then I do not have at least one face card. Awesome. Okay, so I'm going to do the same thing I did before. I'm not going to keep writing my formula. I'm just going to write that I'm looking for N of A. And I know it starts out with a 2 million number, right? 2,598,960. Next time somebody asks you, you'll know, right? How do you get no face cards?
Okay, the face cards.
40C5. So why is it 40, Garrett?
Because you minus the face card.
Right, and we actually mentioned that one at the beginning of class, didn't I? There's actually 12 face cards, right? So there's 52 minus 12. There's 40 non-face cards. So this is subtraction. I've got 40 that are not face cards. Ace gets included there by default. I understand that's a good card, but that's not the point. Okay, and then I'm going to choose 5 of them, right, Garrett? So I've got the C5 there at the end. Okay, I haven't done 40C5 yet today, so we'll do that one. All right, so I have my 2 million number here at the beginning. What is 40C5? What will it look like first?
40 factorial over 5 factorial. 35 factorial.
Good.
Where did the 5 come from?
The 5 came from right over here
I mean, where did you get the 40C5?
because we're picking at 5 hands of cards. I can't have 5 cards. Yeah. 5 cards in our hand. All right, then. I've got my 2,598,960 minus. So what do? I'm going to start with 40, where I'm going to stop. 35. So 40, 39, 38, 37, 36, and 35 factorial. Some of you also had some factorial issues by leaving that off. Don't leave that factorial off. It means something different without it. And then 5, 4, 3, 2, and 1. All right, so I'll reduce my 35 factorial, which was the goal. Now what else?
Looks like we're gonna have to eliminate to get to the run.
I agree.
It's moving a sticking point.
Can you find one to eliminate, Leah?
Well, here's the 5 and the 40 we can get rid of.
Okay, so if I do 5 and 40, what will 40 become?
8.
And 8. Good. Somebody give me another one.
4 and 2 with 8.
Ah, that sounds good. So the 4 and the 2 beneath are actually equal to the 8 that I just came up with. Good. Now what?
Okay, now we're stuck between a rock and a hard place.
No, it's not. It's not hard. It's not hard.
36.
3 has 2 options, right? Which one do you want to use?
39.
39. All right, so 3 and 39, and Garrett, what will the 39 then become? 13. Looks good. All right, so I have a 13, a 38, 37, and 36. So this is going to be a much larger number than I've had on the previous slides. So 2,598,960. What is this number all multiplied out? 13, 38, 37, 36.
638,008.
008. Okay. All right. And then we're going to subtract, right? So what do we get when we subtract this one? Nope, I don't have 2 million anymore, do I? I have 1 million something. Did you not get that? Okay.
658,008.
Oh, okay. So a little bit off. We'll fix.
Oh, sorry.
Oh, that's okay. We'll fix it. Better? All right. 1 million what? What's my subtraction here? 952? All right. Make sense? Okay. Let me try another one. A hand that has at least 1 diamond. What's the complement? Say louder. No diamonds. This is not rocket science, right? But you have to pause and ask yourself, because if you try to actually figure out the at least 1 diamond situation, that is a much more difficult situation. And let me tell you why. If you wanted to figure out the number of ways to have at least 1 diamond, you'd have to figure out the number of ways to have 1 diamond, plus having 2 diamonds, plus having 3 diamonds, plus having 4 diamonds, plus having 5 diamonds. And you'd end up doing this problem in 5 separate stages, then you'd have to add them all together.
Uh-oh.
That's why this complements principle is so friendly, is because I don't have to do 5 different parts to it. I can do 1 part, which is the complement, and then subtract, which is really nice. All right, so I was told what to do, and I didn't write it down yet. Whoops. So this is complement is no diamonds. Is that what you told me?
Yeah.
Yes, no diamonds. Okay, so the problem starts out the same way, right? I still have number of the A and...
What's 52 minus 14? Hold on, let me end this.
Okay, so Leah's going to handle finding out what 52 minus 13 is. Did you find it, Leah?
9. That's 39.
It is
C5.
39. And then C5 because we have what, Austin? Of 5 cards. That's right. We got 5 cards in our hand. Exactly. All right. So I have my 2,598,960. What does 39C5 look like? What goes on top? 39 factorial. Thank you. What goes on bottom? 5 and 34. So how far will I write this out? Somebody say it so I can do it. 34, thank you. All right, 39, 38, 37, 36,
I'm a little bit.
and a 34. I have 5, 4, 3, 2, and 1, and I have 34 factorial. Okay, so the goal being first the 34 factorials go away. All right. Tyler, give me one. What can I simplify on the left, or on the top and bottom here? Sounds good. 5 and 35, so my 35 will be a 7. Excellent. Katrina, can you find another one for me?
2 and 38.
Okay. And what will the 38 become?
18.
Close. 19. Yeah. Another one. Holly, do you have one?
4 and 36.
Looks good. 4 and 36. And what will that become? A 9. Got just one left to reduce in the denominator. CG, do you know which one it would be? Yep, we could do 3 and 39. And then the 39 would become a 13. Right. It'll be 13. Okay. So what do we have now? My goodness. Did you have an answer for me there, Ethan? Or were you telling me the numbers that I had? Yeah, 13, 19, 37, 9, and 7. Okay.
57, 57,
Well, that's a fun number. 57, 57, 57. Did I write that down right? Yeah? Okay. But it's going to be fun when you subtract, too. What happens when you subtract?
5, 7, 57. Well, it's definitely ending up a 1.
That's true. We are going to have a 1. No, we're going to have a 2 here, aren't we?
Oh.
I think we still have 2 million.
Or do we?
What'd you have when you subtracted, Trent?
I got 2,023,200.
230?
203.
2 or 3. 2s and 3s everywhere. So I had 5s and 7s everywhere, and then I have 2s and 3s everywhere, which I think is kind of funny.
And the
Yeah.
zeros. Don't forget the zeros.
That's true. I have the zeros too. 2s, 3s, and zeros. Okay, any questions on that one? All right. We're going to do something else in this section. This is the additive principle. Now let me very quickly clarify the difference between what we just did and what we're about to do now. What you're about to do now is a really easy process, but let me tell you why it's so much easier before you start writing anything down. So everybody stop writing for a second and let me clarify the difference here, and then I'm going to let you write down the difference. We had actually been looking, Austin had asked me why was there a 5 when we were doing all of those combinations, and why was there a 5? Because we were doing 5 card hands, right? As we do this additive principle, we're only going to be picking 1 card. So obviously if I pick 1 card, it's going to be an easier process than if I was picking 5 cards, okay? So when you're looking on this particular problem set in your homework or on your test or my math lab, one of the kickers to making the decision about which kind of one you're looking at, very quick and easy, dirty kind of thing while looking at this, is how many cards am I picking, or how many whatever am I picking? Am I picking 1 or am I picking 6, 10, 5, 12, whatever? because that will help you determine which kind of situation you're looking at. Okay, please, right now. The additive principle of counting says if we have two sets A and B, and you want the items in the union, you can add the number of items in each set together and remove the intersection. And you've seen this before.
Yeah, I've seen it before already.
Back in chapter 2. And then if you have disjoint sets, that means they don't have anything in common, then you don't have to worry about the intersection, because if they don't have anything in common, what's the intersection number? 0. So it just goes away. So as a reminder, I'm going to show you where you've seen this before and why this formula works. You guys remember these guys? What's this guy called?
A circle.
Thanks, Leah. What's this whole picture called?
A Venn
A
diagram.
Venn diagram. Yeah. All right, so if I have A and I have B here in my Venn diagram, in my universal set U, and I add up the number of items inside of set A, that's all of this picture, right? And if I add up the number of items in set B, I get all of this picture. And what happened when I did that? I counted the middle twice. So when I count the part on the left circle and I count the part in the right circle, if I count in this way, I've double counted the middle. So in order to make up for that double count, I have to remove it one of the times I double counted it. So that's where that formula came from when we saw it before. And it works exactly the same way now. Okay, we're removing double counts. So let me show you the actual problems and you'll see what I mean about how it works the same way. So again, look at the example. It says if a single card is drawn, this is not a 5-card hand. Single card is drawn from a 52-card deck. In how many ways could it be the following? So we're going to figure out how many ways it can be, the number of ways it can be a diamond or, remember, or is a union, a diamond or an ace. Well, basically what this should be is the number of diamonds plus the number of aces, and then we should subtract out the numbers that are diamonds and aces. Now, you don't have to write down this notation. I'm going to do it one time, and then I'm probably not going to be writing on the next slide. But that's what we're doing here. You're trying to find the number of diamonds. How many diamonds are there in the deck of cards? 13. How many aces?
And 4 aces.
4 aces. But what happened was I counted something twice. What did I count twice? The ace of diamonds. And there's exactly how many of those? There's one of those. So I need to remove my double count, the one that I double counted. So 13 plus 4 minus 1 is 16. You didn't even need a calculator, did you? Okay. These additive principle ones are just exactly this straightforward. Don't overcomplicate them. There's no factorials, there's none of that. Okay, we're looking at this idea of overlapping sets. This is, you bet, I'm sorry, Colt. So don't overcomplicate what you're asked for. You're not asked to do this for 5 cards. It's just for the 1 card.
Why do you take out the one that you got twice?
I counted the ace of diamonds twice. I counted it when I counted the diamonds, so it's one of these 13, and I counted it when I counted the 4 aces. It's one of these 4. So I've counted it in both of these places, which I shouldn't have counted it twice. So I removed the one time that it was double counted.
So you're just removing the double counting from the additive principle.
Exactly. All right, so we're going to do the same thing over here. We've got a number card and a red card. Okay, so now I specifically said number card here. I didn't say non-face card, okay? So really it is a number card. How many cards in a deck of cards are number cards?
Okay, we're gonna just subtract 12 face cards.
Well, yes, there's 36. Where did you get your 36, Trent?
The face, or, actually, I just took 1 through 10.
1 through 10, and how many numbers? And it's actually 2 through 10, right?
Oh, yeah.
Yeah, 2 through 10, so there's 9. There's 9 in an individual suit, and how many suits?
48.
4, so we get 36. There's 36 of those. So the number cards, there's 36 of. How many red cards are there? 26. But I counted some stuff twice. What did I count twice? The red number cards. So how many red number cards are there?
20.
There's 18, right?
Oh,
Yeah, 18 red number cards. So this 18 here at the end, these are the red number cards. If there's 36 number cards, half of them are red. So that's one way to do it. Or you could actually find that there's 9 in each suit, and there's 2 suits that are red cards. Okay? So what is 36 plus 26 minus 18? Somebody said it. Yep, it's 44.
Oh,
Is that okay?
yeah. I got it up to 8.
Okay. All right, a black card or a diamond?
That's disjoint.
Those are disjoint, right? So if you recognize they're disjoint, you don't have to worry about the intersection. If you don't, at some point when you start thinking about the intersection, you're going to quickly realize that they are disjoint, right? If it's a black card, it certainly is not a diamond because a diamond's red. All right, so how many black cards are there? 26. And how many diamonds are there? 13. And I'm going to put the 0 here just as a reminder to us. You don't need to put it or anything. But these are disjoint, which is causing that to be 0 or causing that to not be there at all, if you want to think about it that way. And 26 and 13 is 30, what?
39.
39. Okay, 39. So I read that one and I think of skiing because black diamonds and stuff. So if you know what I'm talking about, because you've skied before. If you don't, it's okay. All right, last one, number 8. A black card or a club? How many black cards are there? 26. How many clubs are there? There are 13. But what happened?
It looks like we counted twice.
What did we count twice, Leah?
The clubs.
The clubs, right? Because we counted them already with the black cards, and then we just recounted them again. So what would actually go at the end here? It actually would be 13 at the end here. So if I did 26 plus 13 minus 13, I have
26.
26. Now, one thing to kind of make a mention of, so if you don't, I mean, this formula works great, and I don't have any problems with it. You could actually draw a Venn diagram for these too, if you like that method. I know some of you are very visual, and if you want to draw the picture where you did something like, let me do one over here where it didn't have any over.
But
Let's do this one. If I did a Venn diagram for this, for those of you who might be interested in that approach, you would have your diamonds here, and you'd have your aces here, and you'd have to stop and ask yourself how many ace of diamonds are there, and there's 1. And then you can say, well, how many diamonds are there? There are 13, but I've already got the 1 in the middle, so there's 12 out here, right? How many aces are there? There's 4, but I've already got the 1 in the middle, so there's 3 out here. And then you could actually count up the pieces that are there. Do you guys understand that too? So if you like that approach, you could use that instead of this particular formula as a different way of approaching it at all. Okay.
and look,